So I want to recap the second law of thermo for phases. Okay, and the idea here was that the chemical potential has to be same for every component, and I really want to drive this home because we will be using this again and again and again, and I saw some blank faces last time. So what do we want to do here? We have two phases, alpha and beta, and they are existing in equilibrium with each other. And I drew a boundary in the middle, but this boundary could be abstract. You know, there are just two phases which exist. For example, you could have a boundary which looks like alpha is like this, and this is all beta, or maybe they're mixed, you know, some generic boundary where they exist in equilibrium with each other. So suppose two phases, alpha and beta, exist in equilibrium with each other. And let's say they have components 1, 2, 3, ... Okay, so the key result that we proved that a couple of classes ago, that second law of thermodynamics for phases basically says that the chemical potential in phase alpha for component 1 should be equal to the chemical potential in phase beta for the same component. Same thing applies for component 2 in phase alpha, component 2 in phase beta. We are not saying anything about this thing. This we are not saying anything, right? The chemical component, the chemical potential of this in the same phase of two different components, that can be different. There is no justification why they should be same. But for any component, any given component has same chemical potential across phases. This is equivalent to second law of thermodynamics. This is at equilibrium, and this is why we're talking about equilibrium phase diagrams. If we're out of equilibrium, we really don't have anything to guide us. So I want to prove this again because this was so important, and this will help us really stare at it a bit more. So we are talking about equilibrium at a given temperature and pressure. Okay, so this I don't see you guys getting confused with it anymore, but you know, initially it used to be confusing that we are talking about pressure, temperature, phase diagram, and then we are saying given temperature and pressure, right? So we can vary the temperature and pressure, but as we vary it, we focus on one value. So one more. So I will have this. So for why not? I don't have my chair anymore. So for equilibrium at constant temperature and pressure, the condition is dG is equal to 0, right? If it was constant temperature and volume, what should be the condition? Good. Get the chocolate. You don't eat sugar. Oh, sorry. Who?
Do you like soda? No, I put two.
Make it up for it.
Here you go. Here's sugar, right?
So we know dG is equal to 0. So this means where can dG come from? We are talking about two phases, right? So dG can come from the dG due to phase alpha plus dG due to phase beta. The sum of these two must be equal to 0. Now remember, okay, next chocolate question comes. What are the natural variables for G? TPNN. Aiden, more, you don't get chocolate just like that. You have to tell me more. And do you remember? So G is going to be a function of T, T, and N, right? And what is DG? Do you remember?
DG changing its
Mhm. So I'm asking you to fill up things here.
It's the
Correct?
S and then it's
Plus or minus?
minus.
Good. And this was very important, remember, because we use this to show that free energy curves with temperature at constant pressure always go down. Remember?
Yeah.
Because partial G and then this one,
Mu.
you with sugar, right?
Yes.
Good.
They are.
You get 3. So we are talking about constant pressure and temperature. So we can ignore this, right? P is equal to 0, T is equal to 0. So DG. And here we can talk about different components. I is equal to 1 to K. Mu I, D and I. So DG is going to be summation. I is equal to 1 to K. Mu I, D and I. Okay, at constant T and P. So this is for multi-components. Now let's do an experiment where let's imagine transferring. So all I'm doing today is really a recap of things I did, but it is so important that I want to do it really again. Transferring dN1 moles of species 1 from phase alpha to phase beta. Okay, let's call this as equation number 1. DG is equal to summation mu I dni at constant T and P. But now we are saying that dni is non-zero only for 1. Okay, so dni is not equal to 0 for I is equal to 1, and dni is equal to 0 for I equal to 2, 3, 4, ... Okay. What are the natural variables for A, Omar?
A, it's N, B, and T.
Good, you get the chocolate.
We got something for the catch too?
Huh?
I gotta do that. So I gotta talk
No,
to
this is not a cricket or softball class. So, okay, you're late, but you didn't much. We are just trying to recap why second law of thermodynamics, how second law of thermodynamics look for phases. Why is chemical equilibrium same? So we have constant pressure and temperature. So DG is equal to mu I dni summation. And on top of that, we are saying that this dni is non-zero only for component 1. Okay. So what does this mean? Therefore, DG alpha plus DG beta is equal to 0 can be rewritten as mu1 alpha d let's not try to be too rigorous and just think about it. So we have DG is equal to mu1 dn1, right? From equation 1. Because everything else is 0. dn2 is 0, dn3 is 0, dn4 is 0, and we can do this separately for both the phases. So DG alpha is going to be mu1 alpha multiplied by minus dn1. And this is where you have to be careful because we have transferred dn1 moles. We have removed dn1 moles from phase alpha. Okay, so this has a minus sign, while DG beta is equal to mu1 beta plus dn1. Beta phase gained plus dn1 moles. Okay, if it's confusing, just think dn1 as a number. Let's say dn1, let's say we transferred 5 moles. If we transferred 5 moles, that means for phase alpha, dn is minus 5, right? That's the idea. Go ahead.
So up top, the conditions are saying, it's not saying we have one species, it's just saying one species is changing.
Absolutely correct. Yeah. There are many, many species, but at the time we change one. Okay, because that's like calculus, right? That's the whole idea behind partial derivatives, right? We keep everything constant and change one at a time. Multivariable calculus allows us to do this. And now on top of that, we are saying dg alpha plus dg beta is equal to 0. This is the condition for equilibrium. Therefore, mu1 alpha minus dn1 plus mu1 beta plus dn1 is equal to 0. And this is true for all values of dn1, right? It could be true for dn1 5, 10, 50, 40, LF naught, whatever you have. Therefore, mu1 alpha minus plus mu1 beta is equal to 0, or mu1 alpha is equal to, so this is true for all dn1. So we can just remove the dn1. Therefore, mu1 alpha is equal to mu1 beta. So this is the condition for equilibrium, this across phases. Anytime you have a phase boundary, anytime you have two phases existing, the chemical potential for any component must be the same in two phases. If you have more than two phases existing, same thing applies, right? And we did this for species 1, for component 1, but we could easily do the same thing. We could repeat it for changing 2 and keeping 1, 3, 4, 5, 6 constant, right? So we did this a couple of classes ago. This is an easy proof, but it's so important that it was worth it to do it again. Any questions?
So when you're moving some number of molecules from or atoms or whatever from one phase to another, what does it mean? Because a phase is where all the properties of that.
It's a small change.
Right, but how can you be like,
Kill the
sure
experiment, kill the experimentalist in your heart and bring out the mathematician. It's a thought experiment. Man, you would have given such a hard time to Einstein. It is really infinitesimal change, okay? Very, very, very small change.
But you can, okay, that doesn't affect the.
Yeah, so small that it doesn't affect. If you think it's affecting, divide by 2. Still affecting, divide by 2. You know, the smallest possible tiniest change. And there we run into problems. You know, how small do we go? Remember one thing that has been missing in 684. There are 2 things that are missing in 684. What are the 2 things? Omar already got a chocolate. Anyone else? Kinjal, what do you think?
Time dependent.
Time dependence and? True. Third, atoms. We really don't think about atoms, right? It's just like bulk. N tends to infinity, V tends to infinity. I don't give you chocolate. That's not happy enough. So remember this, okay? Chemical potential stays the same. This is what we are going to use in what we do next. Sophia, you had a question. Someone else raised hand. Okay, good. So now what we are going to do. So November 15th, which is the class before the midterm, I would like to do a recap, okay? So if there was a homework problem that you found confusing, that is not clear, send me a direct message on Slack or just post on general that you would like me to go over it. Or if there is a concept that is not clear, you know, we will do as much as we can in 1 hour, 15 minutes. We'll do a review. And we'll probably do one more review before the final. Okay. So what we want to do now is something quite interesting, which is how do we characterize phase boundaries? So we drew that phase diagram, right? Where we had a triple point and we said quadruple point cannot exist, right? And we have a bunch of curves. And we already talked about the phase diagram of water, which had a slope which went in a certain direction. So we want to understand this more in a more rigorous setup is if we have a pressure temperature phase diagram, and if we have said that there is a boundary across the left side of this boundary, we have phase alpha, and across the right side of the boundary we have phase beta. What governs this curve? What is the equation for this curve? Why is it that for water between liquid and solid, it is left facing? And why is it that for other things, it is right facing? How will it look in general for liquid, solid, solid gas, and gas liquid? You know, so we want to understand all this. So in order to understand how this boundary looks like, so we are saying that imagine two phases, alpha and beta, are in equilibrium. And it's a multi-component system, but let's just focus on one component. You can do everything for other component, okay, one at a time. So let's just focus, or even assume, let's assume one component system. The argument really generalizes easily. Let's assume one component system for the sake of clarity. So they are in equilibrium. What did we just study about equilibrium? What characterizes equilibrium? Chemical potential being constant, right? And remember, when we did Gibbs phase rule derivation, we said that the chemical potential really depends on pressure and temperature. Why does chemical potential depend on pressure and temperature? Because chemical potential comes from G, right? And G depends on pressure, temperature, number. And you're talking about a one component system, or you're not talking about change in the number. So it's just pressure and temperature. So at any point along this curve, we must have, let's say this point, and let's say this point. At both of these points, we must have the chemical potential same. So the chemical potential of phase alpha must equal the chemical potential of phase beta over here. Now, when you go to this point slightly up, both chemical potentials have changed, but they must change by the same amount. Okay, that's the idea. So what we are going to do next is to take this into account. So let's say this is point A, and let's say this is point B. And we call this as equation number 2. Equation 2 must be true at points A and B. Again, this does not mean that the chemical potential is same all along this line. The value of the chemical potential is changing, but it is changing by the same amount for phase alpha and say phase beta. So what does this mean? It means that the change that you had as you went from A to B is the same for alpha as it is for beta, right? In other words, d mu, and let's say this is a small change, okay? Let's say we change this by delta T, and during this process, pressure changed by delta P, okay? And basically we want to derive an equation connecting delta P to delta T. That's what we want to do. So d mu of phase alpha must be equal to d mu of phase beta. If they were at equilibrium at A and they are also at equilibrium at B, they must change by the same amount. We are thinking about a single component system. So we can go back from mu to G now, okay? In other words, dG of phase alpha must be equal to dG of phase beta, okay? Normally G and mu are used interchangeably a lot. All you have to remember is number of moles. That's really the only. So never forget that G is equal to summation mu I Ni, right? This relation is important. Anytime you get confused between G and mu, you have to remember this one. So if you're just thinking about one component, it's trivial. Mu is G divided by N, okay? It's just per mole. Alex, you look unhappy. It's not the thermo, right? Okay, good. Well, not good. So dG alpha is equal to dG beta. But what do we know about dG? Aiden just told us, and got a chocolate for it. Okay. Why are you
Here
confused?
mu is the partial, and there you're also able to write mu as you here for a multi-component system.
I'm thinking about one component system.
No,
Forget
I
about
mean,
multi-component.
Yeah, it would be dg's whatever. Even for one, it would be mu dn1, and then you also have it as mu.
If it's a one component system, then G is equal to mu N.
Right, but that expression tells you. So then, if you take dg of that, it would be d mu times n plus dn times mu, right?
But it's a one component system. Where is the dn coming from?
No, because when you have that expression at constant PT, like the DG expression, you have that as.
Yeah, so
UD.
this is 0 in this case. We are not changing n. It is confusing. We have to go carefully. We are not changing n. A chemical reaction is not happening, okay? Only if a chemical reaction was also happening on top of it, then you would have an issue. A chemical reaction is not happening here,
No, I get it.
okay? So a chemical reaction is not happening. It's a one component system. So G for a one component system, mu is G by N. If you had multiple component system, you would think about component at a time and think of it this way. But if a chemical reaction was happening, then things would be difficult. This is why we defined our components the way we did it, to account for all chemical. So we can, work with fake component, which has taken into account things like that. So, okay. So good that you brought it up. So dn is equal to 0 because a chemical reaction is not happening. We are just changing the pressure and temperature. So dg is equal to vdp minus sdt. And we can use this and write it for phase alpha and write it for phase beta, okay? So for phase alpha, it will become volume of phase alpha multiplied by dp, and dp is the same, right? We changed this by delta p, we changed, well, actually, let me call it dp and dt, okay? So v alpha dp minus s of alpha dt is equal to v beta dp minus s of beta dt, okay? We can move all the pressure terms on the left side and all the temperature terms on the right side. So we get v of beta minus v of alpha multiplied by dp is equal to, so v of beta minus v of alpha, and then this one goes to the this side, s of beta minus s of alpha multiplied by dt. Okay, let me write this equation again on the next page. So we just showed, I'm rewriting it. So s of beta minus s of alpha dt is equal to v of beta minus v of alpha dp, or delta s transition, because what is s of beta minus s of alpha? That is the change in entropy when you go from phase alpha to phase beta, right? When you transition from phase beta alpha to phase beta, dt is equal to delta transition v multiplied by dp, or dp by dt is equal to delta transition s by delta transition v. This equation is super important. It's got a name. It's called the Clapeyron equation, not Clausius-Clapeyron. Clausius-Clapeyron is an approximation. We will come to it later. This is known as the Clapeyron equation. And notice that in order to derive it, we actually did not assume ideal gas or van der Waals gas or anything like that. All we assumed is equilibrium. I did it for a one component system. I told you can generalize it to multi-component. I didn't do that because just math gets hairy. And before I know it, you'll all be very, very unhappy. But you have to take my word that it's just the algebra that you have to account for carefully. The equation applies even to multi-component. Okay. So this is telling us that at any given point, if you want to calculate the slope of this phase boundary, if you could do an experiment where you measure the change in entropy and you measure the change in volume. Now, Vedant, you can help me because you are an experimentalist. How would you measure the change in volume? And that should be easy, right? I mean, you just let it happen, right? And see in a constant pressure, you just let it happen. How would you measure the change in entropy? So the question is, how would one measure delta trans S?
So it's a constant n system.
Constant n and constant pressure and temperature. We are thinking about the change as one phase changes to another phase at a given pressure and temperature.
So you look at the Gibbs free energy. Measure some free energy and then find the interface. Assume in that, because you can't.
Let's say the change, yeah, go ahead.
And just measure the heat.
It's the heat. So why is it connected to the heat? You're correct, it's free energy, but you can actually just measure it in the calorimeter. It's happening at a constant pressure and temperature, and we are talking about two phases at equilibrium, right? So when two phases are in equilibrium, so what do we know about ds? ds is equal to delta Q reversible by temperature, remember? And we are talking about change happening at equilibrium, so we can use this equation. We don't have to worry about free energy here because we do have an equilibrium phase boundary. So ds is equal to delta Q reversible by T can be used here because we are talking about an equilibrium phase boundary. So thermodynamics is a funny subject. I mean, many of the ideas here, I think I was first taught Clapeyron equation in high school in 11th grade, you know, in this engineering entrance exams in India, you're just given this equation, you use it, you do something with it. Then you see it in your first year chemistry and you get a bit more insight. Then you maybe see it in your physical chemistry 1 and you get a bit more insight. Then you see it in graduate thermodynamics and really start to connect dots. And it will keep confusing you. These things are confusing. Go ahead, Sophia.
Just what is the word beside the delta Q?
Can be used. ds is equal to delta Q reversible divided by T can be used here because we are talking about an equilibrium phase boundary. You're silent. You have a question? No? Okay, I'll give a chocolate for a question. Anyone has a question? Go ahead.
How do we measure it? It's a reversible process.
In an irreversible process?
Yeah, we would need an irreversible.
Well, we are not talking about irreversible phase diagrams. Phase diagrams are at equilibrium.
But how would we physically do that? How would we measure entropy in that case?
In that case,
Because we know that ds is greater than that, and so we want to know necessarily ds.
how would you measure delta S? So your point is that even if it's an irreversible change, we should be able to measure delta S, right? Because it's a state function, right? So anyone wants to answer Nathan's question?
But I don't think this derivation would necessarily hold.
But he's asking a more general thing. How would you measure entropy change? Yeah, this derivation is only for equilibrium phase time. How would we measure entropy change during an irreversible process? Well, it's a state function, right? So we ignore that process and we construct a pathway where we can go reversibly. So it's like me taking you and like banging your head through the wall, through the roof and taking you to the upstairs. It's highly irreversible, right? It will destroy you. But once you go there and equilibrate, you will have some entropy value. So instead of this pathway, I could imagine a pathway where you gently walk through the stairs and go up. Entropy change should be the same. I will have to kill you at the end of this pathway also, right? So the end states, you must reach equilibrium in both cases. No, this is the nice thing about entropy. Even though it is ds is more than delta Q irreversible by T, you can construct, so, and this is some irreversible path, you can construct some nice reversible path and then go along that one, and delta S should be equal to the same, right?
But it won't, the reversible is the maximum entropy change, right? That's what.
Once you
Gauss
reach
says.
equilibrium at the second state,
Yeah, so but.
then it should be the same.
Right, but does that necessarily mean, but then that sort of violates the Clausius inequality.
No, it
That
doesn't.
says that,
It doesn't.
it says that the maximal entropy change is. for the
It doesn't. You're confusing two heats. It doesn't violate it because the heat change, there is, as Alex showed us in the first class itself, there is no violation of second law of thermodynamics
No, I'm
ever.
not, okay, maybe violation is not the right word, but what I'm trying to say is that if that were the case, then where does that greater than equal to?
You write it down once you go home today and show me, you will find that you're getting confused between the delta Q terms. That's where it comes from. Okay, when you write it down, it will be obvious, take my word. If not, I will start from that next class. But let's continue to this one. So since we are talking about equilibrium phase diagram, we can measure ds as delta Q reversible by T. And for example, now if your phase boundary was alpha going to beta, and let's say it was solid going to liquid, then delta Q reversible has a name for this transition. Anyone remembers what this name is? It's the latent heat of fusion, right? It's the latent heat of fusion. If you had solid going to gas, then what is the name of this one? Sublimation or vaporization, right? So we can measure this, and this is experiment even I have done when I was an undergrad. It's quite easy. So you can measure this and you can characterize your phase boundary. Okay, so this Clapeyron equation is very, very general. We did not assume ideal gas or anything. It applies for any phase boundary at equilibrium. If it's not applying, you're out of equilibrium. Something has gone funky. Okay, so and we will now work through as to how to actually make it more tractable, because delta S, how do you measure entropy? But since it's reversible change, it connects to this one. And this equation will allow us to make practical use of Clapeyron equation. Okay. So the first thing I want to start with is the puzzle of ice skating. I posted a couple of links on Slack. One was from New York Times, one was from Vox, which still says basically, if you go and read it, you will see that it's complicated. People are still arguing over it. But I'm going to show you now that ice skating cannot happen due to the argument of localized melting. It's not that you're putting a blade and it's melting and that's creating a veneer of water and you're going over it. That's not the possible reason. In order to do that, we have a bit more before we get there. So we are going to now we will use actually, before I get to the abstract case, let's just look at ice. Because so the water phase diagram looks something like this. You have a negative sloping curve, a curve over here, and a curve over here. This is the critical point. This in the middle is the triple point. This is solid. This is liquid. This is vapor. In a little bit, after we go through the ice skating example, we will get more intuition into why are these three curves sloped the way they are. Okay, for now, let's just assume that the solid liquid curve is negative sloping. Okay, we'll get to that. Why is it negative sloping in a little bit? But let's assume it is negative sloping. So the way ice skating works is, anyone remember the value of the temperature at the triple point of water? But is it above or below the 0 degrees Celsius? I think it's slightly above. I don't know how accurate it is, but it's slightly above. So let's say this corresponds to 0 degrees Celsius. And then normal ice skating rink is kept at something like -6 or -8 degrees Celsius. Okay. And in fact, if you're in a very cold place, the localized melting argument becomes even worse, as you will see in a moment, because you have to apply even more pressure. So it's best to stay close enough to the liquid solid boundary. So let's say you are at some -7 degrees Celsius, which is a typical skating Has anyone seen do people here know Lake Artemisia is nearby?
Yeah.
Have you seen it frozen yet? It freezes every winter a couple of times. But don't try to skate on it. Apparently, they have found a lot of dead bodies in Lake Artemisia. Yeah, it's true. You can go and Google. So you're at -7 degrees Celsius, which is so cold that at atmospheric pressure, right? I mean, ice skating rink happens at atmospheric pressure, right? I mean, wherever your atmosphere is, whichever place you are. So you're going to be solid. Everything is just solid ice. So the idea in localized melting is that you're applying a bit of pressure on through your skates, which look like sharp blades. You apply a bit of pressure. And as you apply pressure, you get close to this boundary and you enter the solid liquid coexistence region, okay? Because you have applied pressure. If you can do that, you can have you can get close to the boundary where you have solid and liquid existing. So the question is, how much?
Temperature increased while we apply pressure.
Sure, it's thermostatic system. No. You're right. Temperature should increase, but we have a big AC or a heater or something working, so the temperature is kept constant.
Even in the local region.
Very good point. So, but thermodynamics, temperature is a very global property, right? So yes, at the atomic scale, the temperature is getting funky. But we assume that the heater or the cooler is so effective that, this is a very good point. So we have to calculate the value of delta P corresponding to delta T 7 degrees Celsius or 7 Kelvin, right? That's what we have to do. That's another advantage of using Celsius. You can, delta T in Celsius is the same as delta T in Kelvin, right? It's not true for Fahrenheit. Yeah, Fahrenheit is a terrible scale. So, and let's say this pressure is 1 bar, okay? So now we have to calculate delta P by delta T. What did Clausius equation tell us? That is delta S transition by delta V transition, okay? So that is delta S by delta V. And I said, this is all reversible. We assume everything is in equilibrium, which answers your temperature question because we assume equilibrium at any point, right? So delta S by delta V is going to be delta Q reversible by temperature divided by volume, and delta Q reversible in this case is the latent heat of fusion, L. So this is L divided by T divided by delta V. So we need the values of 3 things, and that I will provide you from an experiment someone did. So L for water and ice is 3.34 into 10 to the power 5 joule per kg. T is minus 7 degrees Celsius, so it's around 267 Kelvin, okay? How about delta V? When you go from solid to liquid, is delta V going to be positive or negative?
Can you just explain how you got from delta S?
Delta,
Sorry, I got it. It says
Yeah.
delta Q.
yeah. So delta V is positive or negative? Someone who has not answered, I have 3 chocolates left. Yeah? Solid to liquid.
Solid.
When ice melts, does the volume go down? Or let's think about it the other way. I just mentioned it to you, Lake Artemisia freezes. Where does the ice go, on the bottom or on the top? On the top. So what does it mean for V liquid minus V solid? Is this going to be positive or negative? Negative. Money chocolate. So this is negative. And it is at around minus 9, 10 to the power minus 5 meter cube per kg. Why is it negative? That's something we cannot answer using thermodynamics, but does anyone know?
Hydrogen bond.
What about hydrogen bonding?
It's when you look at liquid water, it kind of looks a lot like solid, at least locally.
Yeah, that's correct. So liquid water has some local hydrogen bonding, which is actually more ordered than the ice itself. Which one do you want? Money? Good choice. Sorry. So yeah, it's the hydrogen bonding nature of water, and that's why other liquids don't have it. But what? Why are you making fun of my chocolate? Go ahead.
The rate of fusion depend on
That's Kennedy.
temperature.
It does, but we take some approximate value. Okay, so if you put these numbers together, we get delta P by delta T is equal to minus 13.5 megapascal per Kelvin. So in order to change the temperature by 1 Kelvin, you have to apply 13.5 megapascal pressure. Therefore, to change T by 7 Kelvin, we need approximately close to 100 megapascal pressure. Does anyone have a feel for 100 megapascal? What is atmospheric pressure?
About 101.
Huh?
101.
But what's the unit?
101,000 pascals.
I think it's step up by 10 years. It's 1 megapascal.
Anyone has a phone? Can you check and confirm to me? How much is atmospheric pressure in megapascal? I know it's 1 bar. I think it's much smaller than this, but I want to check.
It's of the order of 10 power 5.
It's 10.5 Pascal, which is 2.1.
Yeah, so so pressure atmospheric is equal to 10 to the power 5 Pascal, which is how much? Which is 0.1 megapascal, right? So you have to apply 1000 atmospheric pressure for this idea to work. That's a lot.
Yeah, not bad.
You will have to weigh as much as an elephant and have like ballerina shoes. That's the only way I can think of it, so it's an elephant. No, I was thinking, but I tried one time and it didn't work. Elephant in ballerina shoes. Okay, so it's not going to work. So ice skating does not work from localized melting. When you go and read the articles I posted, you will see that it is kind of localized melting, but it's a nanofilm of water. So you might say, well, then it is melting. But then the problems that Kinjal was pointing out come into picture, right? If it's a nanofilm, it's no longer equilibrium. You basically have to go out of equilibrium. You cannot explain it using equilibrium thermodynamics type argument. It is kind of like melting, but just one film, like a nano, two atomic layers of water form. That's how thin it is. So good. So you can see these things are useful. But now we have to really think about these boundaries. That's what we want to do next. So we will basically keep working with this equation, delta P by delta T is equal to delta S by delta V, and try to understand why are the boundaries between phases the way they are. Any questions? Okay. So what?
Stupid joke.
Okay. I have a lot of stupid jokes. I can tell you one. What did the Buddhist ask for at the hot dog stand? Anyone knows the answer? Make me one with everything. What do you call a singing laptop? Adele? Good. So let's look first at solid liquid phase boundary. Okay. So once again, we have dP by dt is equal to delta S by delta V, and delta S is equal to delta Q reversible by temperature. So this becomes, what is the, yeah, go ahead, Sophia.
Is this still for water?
No, now we are very generic. Water will be a subcase of this. And let me write here in general. Yeah. So delta Q reversible for solid to liquid change is known as heat of fusion, okay? Divided by temperature and divided by volume change during fusion. So delta S, what we did here is to say that this is, we used delta S is equal to,
What is the subscript?
fusion, FUS, heat of fusion. For most things, in order to go from solid to liquid, do you have to heat it or cool it? Is there a counterexample? Huh? Nope. Feynman did a lot of work on it. Helium-3.
Helium,
Yeah.
close to 0 W.
It's become super fluid and all those things. It's very funky. So delta fusion H is more than 0 for almost everything, including water, except helium-3. And I don't understand why it is true for helium-3. I don't think anyone understands. There are models to explain it, why it goes like. It really conducts to superfluidity and superconductivity, where superconductivity is one of those problems where some experimenters once told me that if a theorist makes a prediction, they will go and do the exactly opposite thing, and they have a higher chance of succeeding. The theory is so bad still about it. I'm not going to say anything bad about quantum computing, but anyway. No, there was a lot of hype about high temperature superconductivity in the 80s and 90s, right? And it never took off. And it's natural to question, are we witnessing the same hype with quantum computing? Because trillions of dollars are being invested into it, and no quantum supercomputer really exists, which can work with like more than one or two things. So it's natural to be critical. And I find it odd because it often gets conflated with AI, while AI has really taken off. There is no question that AI works. Whether you want to call it AI or not, that's another question, but machine learning works. We all use it all the time, right? Every day. Okay, so let's get back. So helium-3, I don't know why it is that heat of fusion is negative, but for almost everything, it is positive. Volume change during fusion.
This H is the same, it's enthalpy or?
Yeah.
But
We are talking about
constant pressure processes have heat and enthalpy the same, right? So
yeah, we just call it enthalpy. It's not volume. Yeah, go ahead, Patrick.
What's the difference between L and delta H?
There is no difference. There is no difference. The latent heat of fusion. L is more general, I guess. There is no difference. So delta volume of fusion, except water, most things, when you heat them, they melt and they expand, right? That's the general feature. Do they expand a lot? Not really, right? Maybe 5%, 10%, maybe 20%, right? So I'm going to write it as positive, but close to zero. It's not going to be super positive. You won't see a change of 100 times. This will matter when we go from solid to gas, right? Sublimation, things change drastically. Except water, where delta fusion V is negative. So what was the number of our equation? So let's call this as equation number 4, the Clapeyron equation. And let's call this one as equation number 5. It doesn't really matter. Therefore, equation 5, this is always positive. The numerator is always positive. We are not going to worry about helium-3. The denominator is positive for everything except water, right? So what does it tell us? It tells us equation 5 implies that dP by dt is positive for almost everything, and dP by dt is negative for water. So now we can explain why was the curve, the phase boundary in the water phase diagram the way it was. So this means that if you plot a pressure temperature phase diagram, the slope of this thing, and if this is solid and this is liquid, it's going to be a positive sloping line. Furthermore, this denominator, delta fusion of volume, is positive, but it is not super large, right? It is close to a small number. That's why this curve that I drew over here is almost vertical. Okay, it's positive sloping, but close to vertical. I did not draw, for example, a curve that looks like this. This is more likely because denominator in equation 5 is close to 0. This is less likely. It is still possible if you have something where the volume change is huge. It is possible that slope is close to 0, but most of the time it won't be. And this positive sloping curve is true for everything except water. Water will look like this. Okay, it will be again close to vertical, but negative sloping. Okay. And why did we have delta fusion be negative for water? That, as Patrick answered, is the hydrogen bonding. I mean, we are not really covering it here, but it's local water has structure. And people still argue over it. Why does water have structure? You can go and read. Yeah. Water conferences are the most intense conferences. People just fight and fight and fight. Okay, any questions about this?
How do we get the curvature? Because the lines on the graphs you can draw are not straight.
Yeah, I don't know about the curvature. I just talk about the slope in the local space. You're right. I don't know how to calculate the curvature. Sorry. Okay, we did solid liquid. So we have three things, right? Solid, liquid, and vapor. So we want to talk about three boundaries. We did solid liquid. Now let's move to liquid vapor. Similar idea, but the signs will be different now, okay? Because we have to look at the delta term carefully. So let's now look at liquid vapor boundary. So once again, dP by dt is equal to delta S by delta V, but now it will be delta H of vaporization, right? VAP, divided by temperature of vaporization multiplied by a delta VAP volume change. So delta VAPH is latent heat of vaporization. Delta VAPV is volume change during vaporization. So once again, and I think this is true even for helium-3, is that delta vaporization of heat is definitely positive. I don't know of any chemical or material where you have to cool it to go from liquid to vapor. You have to heat it to go from liquid to vapor. How about delta VAP volume change? So let me write it down carefully. So we are talking about volume of gas minus volume of liquid. Is this going to be positive or negative? Aurelia, what do you think? Positive. Do you think this will be less positive or more positive? Sorry, which one was it? Yeah, this. Then, so we also saw that for almost everything else, when you heat it, liquid has more volume, right? Except water. So Aurelia, what do you think? This top one, will it be more positive or less positive than the one on the bottom? More positive, right? And especially for hydrogen, something like that, it will be crazy positive, right? Good. You got it up. Last one. Part 3. So don't worry, I'll have more next time. So this is going to be much more positive than 0. So once again, what does this tell us about the slope? The value of dP by dt. This is positive. This is also positive. So dP by dt is always positive. But the denominator is now a large number than the previous time. So the value of the slope itself is going to be a bit smaller. So if you go to our phase boundary, our phase diagram, and I will ignore water for a little bit, okay? I will just draw or actually I will draw both. So most things is something like this. Water is something like this. So this is water. This is so pressure and temperature. Almost everything else and this was our solid liquid boundary. And now we are talking about liquid vapor boundary. So the slope of the liquid vapor boundary curve is also positive, but it's less positive than solid liquid. Okay, so it's going to look something like this. Okay, and this is our vapor. So as you can see, this one This one over here is very steep. While this one is less steep. That's the idea. Okay, so we have got solid, liquid, vapor, and we have to think about the third one, which is the solid and vapor boundary. Okay, go ahead, Patrick.
Why isn't the liquid vapor basically almost flat?
It should be.
Okay.
It should be.
But we didn't comment anything on delta vaporization on both the cases.
It's just positive. We don't know much else. It's positive. We don't know how exactly to calculate the value. I don't have intuition for it. Volume, I have intuition. H, I don't know. Right. So that could change the picture. You're right.
And also, how do we understand which side is which? Vaporization is in the top, vapor side is in the top, or is in the bottom?
That again, well, the best way to understand it is at a given pressure, you go from solid to liquid to vapor, right? You know, at 0 Kelvin, everything is solid, right? There is one ground state. Quantum mechanics tells us this is ordered structure. So we start from solid. And actually we thought about this when we did that. Remember, we did the 3 straight lines where we used dg is equal to vdp minus sdt, and we showed that the free energy must be going down as you increase the temperature. That's where we showed why solid goes to liquid to vapor. Good. So now let's think about this third one, which is solid vapor phase boundary. Okay, and then this would be our triple point. So finally, same equation, just looking at things again. Solid vapor boundary. So now we have dP by dt is equal to delta sublimation H divided by T delta sublimation volume. Okay. And once again, it takes heat to sublimate something. This is positive. And delta sublimation volume, which is V gas or V vapor minus V solid, this is also a very positive number. It's a very large number, right? So once again, the slope dP by dt will be positive and almost flat. Okay, so let me draw it once again. If we have our phase diagram, we have solid, liquid, something like this. And again, like Ethan pointed out, I'm not talking about curvature. I'm just drawing straight lines because I have not derived anything about curvature. Most of it will almost certainly be curved. This and something like this. So it's going to be solid, liquid, vapor. And this over here is known as, so this is pressure and temperature, triple point. And this is critical point, which we'll study about next time as to what actually happens here. A little bit, we're not going to too much detail. Yeah, right.
In a single component system, can you have only 3 phases?
Yeah.
So you can't have, there aren't materials that have
Mm.
solid.
Oh, you can have 50 phases. Ice has 15 phases at least. They cannot coexist at the same pressure and temperature.
So you won't, so you don't draw the phase diagram, so you can't draw a phase diagram for ice then.
I can, but at any point, it's like, imagine a map of the world where 4 countries have border. I'm saying that cannot happen. It doesn't mean the world cannot have 50,000 countries. It's just that 4 of them cannot share a border.
No, like my point is that like if for 2 component systems like iron or carbon, you have like solid, liquid phase, and then you have all those random.
Yeah.
But here we're just assuming that
Here, if you're just assuming 1 solid, 1 liquid, and 1 vapor, this is how it looks like.
yeah, that I agree.
But if the solid itself has more phases, if the liquid itself has more phases, you can have some crisscross geometry inside this.
Okay.
If you go and look up, I recommend all of you to go look up water phase diagram. You will see how the solid is actually a whole jungle. It really splits into complicated geometries. It starts to look almost like the iron carbon phase diagram. But this is always true. Any single component system can at max have a triple point. This does not mean a single component system can have only 3 phases. It can have 500,000 phases. At the same pressure and temperature, at best, you can have 3 of them coexisting.
But
Okay.
would you use the same arguments for those phases?
Absolutely.
The DP.
Absolutely. I did it only for 3, but I could start talking about ice 9 and ice 11. It's the same idea. You just have to calculate delta S. And this is for water. This is going to be negative sloping. And this is everything else. Go ahead, Patrick.
Yeah, so if you start out in the solid regime or phase and raise the pressure enough, and for water at least,
Mhm.
it would go back to being a liquid.
Absolutely.
Yeah, that doesn't make any sense.
Why not? You are at a certain temperature and you start increasing pressure. Have you tried applying pressure on an ice cube?
No.
You should go home and do it. It becomes water. Why is it that you can join 2 ice cubes together by applying pressure? It's the same idea, right? Like ice skating. When you apply pressure on ice, it becomes water. You really gotta go and do it today. Go get something from soda machine and apply, put crunch on the ice in your mouth. It becomes water, right? Or you're swallowing ice
I
cubes.
assume that was always from just the heat from.
No, this is due to the negative slope. For almost everything else, if you apply pressure, life is, so water is the one that we are accustomed to, right? Because that's the thing we mostly deal with. And we are so accustomed to it that what actually you're more shocked about is everything else, where if you keep applying pressure, it won't become liquid. That is bizarre, isn't it?
So by applying pressure, we can convert from vapor to liquid.
Yeah.
Yes.
But not from solid to liquid, which is bizarre. So, in fact, no, funky things happen. So if you go and look up the phase diagram of elements involved in the core of the Earth, you will see that as you keep changing, the core of the Earth has very high pressure, right? And it undergoes solid to solid phase transformation. And then it's even more interesting because the middle of the Earth's core is actually liquid with a solid floating on top of it. So it gets funky, it gets funky. And also remember, this is a 1-component system. Almost everything is not a 1-component system, right? You have multi-components. So this type of picture can start to change. Okay. We will look at more phase diagrams, but this is very robust. This is true for a 1-component system. I want to derive one more equation and then we are done today, which is a simplification of the Clapeyron equation, which applies only for liquid vapor boundary. Let's restrict attention to liquid vapor boundary. Okay, so what did we do for liquid vapor? We said that it's going to look something like this, right? It's positive sloping, almost kind of flat. And we said that dP by dt is equal to delta vaporization H by temperature multiplied by delta vaporization volume. This is exact, right? This is true for anything. We did not assume ideal, van der Waals, anything. This is any material. Now, let's assume ideal gas. And let's look at delta vaporization volume, which is V gas minus V liquid. And we know this is a very large number, but on top of that, let's assume this is approximately V gas. It expands so much that we ignore the liquid part. Okay, so we are making assumptions now, which we did not do for Clapeyron equation. And we are assuming an ideal gas. And let's assume 1 mole. Let's not worry about the molar. We'll just multiply by number of moles later. So this is going to be RT by P, right? If we assume an ideal gas. So therefore, what is the number of this equation? I don't know, 6 or something. This is equation 6. So 6 implies dP by dt is equal to delta vaporization H divided by T multiplied by RT by P, right? Because this delta vaporization V, I'm replacing by RT by P, right? So I put that RT by P over here. Or dP by dt is equal to P by RT square delta vaporization H. Or dP by P is equal to delta vaporization H divided by R multiplied by dt by T square, right? And now a final algebra, we can write this as d ln P by dt. So this is d of log of P, right? And we take this dt and bring it to the left side is equal to delta vaporization H by RT square. This equation also has a name. This is known as the Clausius-Clapeyron equation. Okay. This, number one, things to keep in mind, is less exact than Clapeyron equation. Because Clapeyron equation, why is it less exact? Because we assumed ideal gas and we assumed that V gas minus V liquid is approximately V gas. So this is an approximation, but people use it a lot. Go ahead.
Shouldn't this work for solid vapor too?
You could, but the Clausius-Clapeyron equation is defined only for the liquid vapor. People don't use it for solid vapor. The reason they don't do it is because people use this. One of the homeworks later on will be a paper, an actual scientific paper that you will be split into groups and you will be doing like a presentation on it. And there you will see how, for example, in protein biochemistry, people use Clausius-Clapeyron equation all the time. Why? Because they can use it to calculate the melting temperature of a protein, right? So this, I was at a protein folding conference last week. It was crazy that experimentalists who, don't judge me, people who have not taken thermodynamics at a graduate level, who routinely confuse enthalpy with free energy and internal energy, were still blabbering about the Clausius-Clapeyron equation because it is so important in proteins. But it's an approximation. You could derive something like this for solid vapor also. It's just that it's not very, you don't care about sublimation of proteins as much, right? It's kind of bizarre. Any questions?
Why do you have vaporized proteins?
Don't, that's what I'm saying. Omar wants it.
So why are you looking at the liquid vapor?
Oh, good point. Yeah, my argument is defeated. When I give you the paper to read, you will see why people care about it. But for now, I just wanted to derive it because you will see it every once in a while. If you forget about what is Clausius-Clapeyron, that's okay. It's an approximation. What you should remember is the Clapeyron equation, because Clapeyron equation directly followed from equating the chemical potential, right? We did a lot today. Next time I will recap it a little bit before I start with critical points. So in order to derive the Clapeyron equation, I look at a phase boundary, I equated the chemical potential. Then I said that we are not having a chemical reaction, nothing is going on. So d mu is equal to dg because we are thinking per mole of a simple system. dg is VdP minus SdT, right? If we have VdP minus SdT, then we directly get the Clapeyron equation, which is dP by dt is delta S by delta T. That's something you should remember. This derivation should be clear in your head as to how we do it, okay? So next time I will recap this because this is important and it was a lot of material, and then we will talk about critical points as to what really happens at this top point over here. We will look at the van der Waals equation of state and try to use that to get an intuition. Effectively, the surface tension between liquid and vapor disappears and the liquid and vapor start to coexist together. Okay, so see you Tuesday.